The term Big Bang often brings to mind a giant cosmic explosion, a single fiery event that created everything from nothing. But this common picture is fundamentally wrong. The Big Bang wasn't an explosion in space. It was the expansion of space itself. To understand this, let's step back in time. In the early 20th century, astronomers believed the universe was static and unchanging. But observations by astronomers like Edwin Hubble completely shattered this idea. Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This observation, known as Hubble's law, was the first major piece of evidence for an expanding universe. If the universe is expanding now, it must have been smaller in the past. If we rewind this cosmic movie, all the matter and energy in the universe would be compressed into an incredibly hot, dense state. This initial state is what we call the Big Bang. It wasn't an explosion happening at a specific point in an already existing space. Instead, it was the beginning of space and time themselves. Every point in the universe we see today was part of that initial state. Think of it like the surface of a balloon being inflated. As the balloon expands, every point on its surface moves away from every other point. There's no central point of the expansion on the surface itself. The expansion is happening everywhere. Our universe is similar, but in 3 dimensions. Every galaxy is moving away from every other galaxy, not because they are flying through space, but because the space between them is stretching. This expansion model explains a crucial piece of evidence: the cosmic microwave background, or CMB. This is a faint glow of radiation that permeates the entire universe. It's the afterglow of the hot, early universe, predicted in the 1940s and discovered by accident in 1965, when the universe was about 380,000 years old. It had cooled enough for atoms to form. This allowed light to travel freely for the first time. The CMB is that ancient light stretched by the expansion of the universe over billions of years into the microwave part of the spectrum. An explosion model doesn't naturally predict this uniform, all-sky afterglow. Another piece of evidence is the abundance of light elements. The Big Bang model accurately predicts the proportions of hydrogen, helium, and lithium created in the first few minutes of the universe. The intense heat and density of the early universe acted as a primordial nuclear reactor. The calculations based on this model match what we observe in the oldest stars and distant gas clouds with remarkable precision. A simple explosion wouldn't account for these specific elemental So, where did the term Big Bang come from if it's so misleading? It was actually coined by astronomer Fred Hoyle in a 1949 radio broadcast. Hoyle was a proponent of the rival steady-state theory, which proposed that the universe was eternal and unchanging, with new matter constantly being created to maintain a constant density as it expanded. He used the term Big Bang dismissively to describe the competing theory. Ironically, the catchy name stuck, even though it paints an inaccurate picture. The initial state itself, often called the singularity, is a point where our current laws of physics break down. General relativity predicts a point of infinite density and temperature, but physicists believe a theory of quantum gravity is needed to describe what really happened. It wasn't a point in space, but the point from which space itself emerged. The expansion that began with the Big Bang continues today. In fact, observations of distant supernova in the late 1990s revealed something astonishing. The expansion is accelerating. This acceleration is attributed to a mysterious force called dark energy, which seems to be pushing the fabric of space-time apart. Dark energy makes up about 68% of the universe, yet we know very little about it. It's one of the biggest mysteries in modern cosmology. Then there's dark matter, which accounts for about 27% of the universe. It doesn't emit or reflect light, but we know it's there because of its gravitational effects on galaxies and galaxy clusters. Without dark matter, galaxies would fly apart, and the large-scale structures we see in the cosmos wouldn't have formed. The ordinary matter that makes up stars, planets, and us is less than 5% of the total content of the universe. The Big Bang Theory is not just a guess. It is a robust scientific framework supported by decades of detailed observations. It describes the evolution of our universe from a hot, dense state to the vast and complex cosmos we see today. It explains the recession of galaxies, the existence of the cosmic microwave background, the abundance of light elements, and the formation of larger-scale structures. The idea of a sudden explosion in an empty void is simple and dramatic, but the reality is far more profound. It's a story of space itself unfolding, of time beginning, and of a universe evolving over 13.8 billion years. The Big Bang was not a moment of destruction, but the beginning of an incredible process of creation and evolution that has led, eventually, to us. Understanding this distinction is key to grasping our true place in the cosmic story.